Thank you. Sorry, I'm muted. Am I unmuted now? Yes. That's going up and down. Perfect. Okay. Well, what I was saying was just review of our introduction to the twitch, saying that we're starting out by comparing isometric and isotonic twitches for everyone online. Okay. So we were starting with the isometric twitch last time at the end of class. So we have in our isometric twitch, we're still going to have our contractile elements. So our sarcomeres, our actin, and our myosin are going to be sliding past each other, making our muscle fibers overall shorter. But we have other things at the ends of our muscles, specifically tendons. So the overall length of like a named muscle here is not going to change. And this happens when our load is too heavy for our muscle to move. Okay, so our load is greater than the tension that we might measure in a muscle. So instead of shortening, the parts of the muscle that are elastic, like the tendons, are going to stretch as the fibers, the sarcomeres shorten, but overall the load won't get lifted. So we saw a picture of that at the end of last time. Okay. So here we see a muscle. So we see a muscle belly where we would have our sarcomeres, our muscle fibers. And when we talk about the elastic element, that's the tendon at the end. So this white part is tendon, okay? So what we're saying with our isometric muscle contraction is that this muscle belly part, where we would have the sarcomeres, did shorten, right? It shortened, but our overall length of this named muscle didn't shorten because our load is too heavy. So this part just stretched out as that muscle belly shortened. So overall, our total distance from end to end didn't change. So this would be an isometric muscle contraction. If we were measuring the force in the muscle, though, we would still see a force, right? The muscle is still trying to pull that load. It's just not overcoming the load. So we would still see a latent phase. We would see tension increasing and then tension decreasing as the muscle relaxes. Okay. So the load would not move, but that doesn't mean that there's no tension in the muscle. Okay. So in an isotonic twitch, we're going to see something different. We're going to define an isotonic twitch as one where the tension is greater than the load. So this means we are going to move something. Something is physically, visibly going to move. Our load, our thing we're carrying is going to move. Going to move because the muscle is going to actually be allowed to shorten now. Right. So isotonic twitches, when this happens, we're going to see that there's going to be a time where we have constant tension. So let's take a look at what we mean by that. Okay. So we have the same diagram, but now it's for an isotonic muscle or twitch. Okay, so we have a load here at the bottom. So this is the thing that we are trying to lift. And we're fixed up here at the top. Okay, so this is that original distance we were looking at from the previous one. Okay, we still have a muscle belly where we would have our muscle fibers, our sarcomeres, and we still have tendons at the end. Okay, so this time when we have our twitch, as this muscle belly contracts, our load is light enough so that the entire muscle is contracting. All right, so the muscle is actually shortening now, meaning we are lifting this load, right? So that's what makes this an isotonic muscle contraction, is that we have actual movement of the load here. Okay. So we could map the tension. So this graph on the bottom is the analogous graph to our previous tension graph. So we have our time on the x-axis, our tension, or basically our force on the y-axis. So we contract, we have our latent phase first, then we have tension increasing as we're forming those cross bridges. Okay. Now, why do you think we see this flat part here? Oh, this is different from our last image. Before we had a big old curve, now we suddenly have this plateau. What do you think is happening during the plateau? This is the constant tension part, right, from that previous slide, the bullet point. So what's happening here, right? Constant tension, that's just a description of this flat part. So this is where we're moving the load. right? So we've reached an amount of tension where the muscle actually starts to shorten, where it actually starts to shift the load. So that's what we're seeing here. So during this phase, we'd have our load actually moving. So we don't need to keep increasing and increasing and increasing tension because we're actually now moving the thing. So that's a good amount of tension to lift our load. So that's why we have this second graph here up at the top. So what we're looking at the top is how much this overall muscle shortened. So we're looking at the difference in the position of this load, right? Like how far it went up, because that's also telling us how much shorter this muscle got. So you can see that when we reach that constant tension time, that's when we are having the actual shortening, the measurable shortening of this muscle in millimeters. Okay, so during this plateau where we have constant tension during our isotonic muscle contraction, okay, we see shortening of the muscle here. So we can see it's getting shorter and shorter and shorter. And then as it relaxes, eventually it gets longer again. Okay. Actually drew the line in a slightly confusing part, so let me do that. So it's getting shorter. It is still getting shorter, but less shorter here, and then it relaxes. So during normal muscle activity, you're probably going to see both of these things happening in concert, right? Some purely isometric contractions do happen, right? So you can think like posture, maybe, right? Like there are some muscle contractions where really the point is to not move. But when we think about isotonic contractions, it's usually going to be preceded by an isometric contraction. So there's usually going to be an isometric contraction first, where your load is too heavy, right? So the load is not moving. And then eventually you'll hit the phase where your force in the muscle is enough to move that load. Okay. So this is just because of that sort of comparison of load versus tension, right? So if we were defining these mathematically and our isometric is that the load is greater than tension, obviously that kind of has to happen first. Okay. So an isometric contraction could happen and then the isotonic contraction would begin. Okay. A thing to know is that from the perspective of your body, load isn't generally constant. Which isn't to say that like if you lift a bucket, right, somehow the bucket is changing overall from the perspective of the bucket. What we're saying here is that load as your limb position changes. If you were to draw out like a physics force diagram, that load is going to change from the perspective of your body, like how much force is weighing down your muscles or something. So you can think about like how hard it is to lift something with your hand fully outstretched versus if it's near your body, right? That's different amounts of hard. Part of that is because the load is changing as your limb position changes. So that is helpful to understand as we're living our lived experiences and thinking about these contractions. Okay. Now, to figure out how much force is generated by our individual muscle fibers, we do have some factors that are going to affect this. One is going to be how many cross bridges are binded, right? So if you make more cross bridges, you get more tension, you get more force, right? You're sliding more, you're sliding harder, you're sliding faster. Okay. Other thing that's going to affect the tension of your muscle as a whole is how many fibers are contracted. And if you contract just one fiber, not going to be that much effect on a whole big muscle, versus if you contract all of the fibers, that's going to produce more force. So we can also talk about how frequently this muscle is getting signal from our nerves. Okay. So when we're looking at that signal from the nerve, what's happening? The signal originally is an action potential, right? So that's what this stimulus essentially is. So each of these pink arrows is an action potential coming down our somatic efferent motor nerve to our neuromuscular junction, initiating contraction. Okay. Now, what we can see is that when we have these stimuli, so action potential 1, we get some amount of tension, then our muscle relaxes, Action potential 2, we're going to get a little more tension, then our muscle relaxes. So basically your muscle is warming up, right? Like this is actually happening. Your muscle is actually warming up, able to generate more force in response to subsequent action potentials. Now, eventually you are going to hit a maximum amount of force generated, right? So eventually you're going to fully warm up, and then each action potential is going to generate that same amount of force. So this plateau is something called trepping. So hitting that maximum force with each action potential after your muscle has basically warmed. Now we're going to think about summation. Okay. So the basis for the summation is that each action potential takes about like 2 milliseconds to get there. Each contraction depends how long that lasts, right? So we have a lot more of a variation there, but we're going to say like 10 to 200 milliseconds for contractions, which means that if you're contracting your muscle, an action potential from your nerve can absolutely come down to that muscle while you are already contracting that muscle. So this is different than that refractory phase that we saw in our neuron-to-neuron communication in the nervous system itself, right? Because now when we're coming into a muscle, we may be signaling to a muscle that is already contracting. This means that our contractions can overlap and they can sum together, making bigger contractions. So that's the basis for this concept of summation, right? So really just addition. So when we have an action potential, first the action potential happens during that latent phase, right? So we're waiting during this latent phase to start our cross bridges. Over time, our tension is going to increase. Then we have our relaxation phase, which is a bit longer as our calcium unbind, lets go of our troponin complex, allowing the tropomyosin to cover over our actin or our myosin binding sites on the actin. Okay, so that's our twitch. That's how it's responding to the action potential. Okay, and now we see what happens when we have multiple action potentials working together. Okay. So we see one twitch just produces that one curve. So that's what we were looking at. All right. So here we see summation and treppe kind of like working together, working up to it. So we see with each action potential, we're increasing the amount of force until we hit this force, right? So that has to do with the treppe part. What we're seeing with the summation, right, is we're not completely relaxing, right? So that's also helping us increase here. Okay. Then we hit a point right here where we see all these peaks here. We're not fully relaxing, but we're hitting that same peak over and over and over again. And then we can hit something called complete tetanus, where you kind of lock out the muscle, right? And it's not relaxing at all in between these action potentials. Okay. All right. So we have a complete, just like clenching of this muscle. So you ever gotten like a tetanus shot, right? This is preventing a disease that causes this, a response in your muscle, right? So if you think about like completely contracting up, I think that's what happens if you like actually get tetanus. Okay. So a couple more things about our muscle fibers that can affect how much force we're creating. So we said number of cross bridges makes a difference. More cross bridges, more force. We said that if we activate more muscle fibers, also more force. A couple more things. We can also think about the fact that we've just been looking at like a single sarcomere or at most like a chain of sarcomeres, but our muscle fibers are actually three-dimensional, right? So you could cut them across. So we're going to have more sarcomeres potentially if we look deep through that muscle in 3 dimensions. So in the first couple slides, right, when we looked at a muscle fiber, what I'm saying is like, we had something like, here's our fiber, right? This is our cross section. We saw that there were dots throughout. So that's really what I'm saying, right? So you can have different amounts of sarcomeres like sitting on top of each other within the fiber. Yeah. So if you have more of them, sitting across the fiber like that, you're also going to create more force. Okay. So this means that our fiber diameter can vary, like, so the diameter, like how thick across that muscle fiber is not constant. So you might have like a really skinny little muscle fiber, you might have a big fat muscle fiber. How big a sarcomere is, like how much space that takes up, is pretty constant. So that's the number of thick and thin filaments per area is constant. So in order to have more sarcomeres in parallel, right, so next to each other, you just have to make the muscle fiber wider. Okay. You're not going to squeeze the thick and filaments closer together to fit more. So this means that a bigger muscle fiber, as you increase that diameter, is going to have more filaments, more sarcomeres next to each other, essentially, and therefore more force. So, super surprising fact, right? Bigger muscles are stronger, right? That's basically what we're saying here. Okay. All right. So for our fiber length, exactly how like stretched out your muscle is also going to affect the amount of contraction you can have. All right. So your fibers operate in a way that like they have an optimum length, so like a position at which your muscle is strongest and able to generate the most force. But that doesn't mean that's the only position your body can be in, right? Like you can stretch out a muscle fiber too much, or you can cram it like way too close together, right? And either of those situations is going to make it harder for your sarcomeres to generate more force. Okay. So if you're at the optimum length at rest, that means you're going to be able to generate more force than if you are not at the optimum length. The optimum length is dependent on like the position of the actin and the myosin relative to each other. So we want to have the ideal kind of amount of overlap between the cross bridges on the thick filament, which is our myosin, and the thin filament, which is the actin. So at rest, hopefully we're at optimal length, right? Able to generate the maximum amount of force, but we could like stretch way out. It's just going to be harder to lift stuff, or it could be like way in, scrunched up a little too much, also harder to lift stuff. Okay. So when we have a greater than optimal length, if our muscle fiber is too stretched out, we're decreasing the amount of cross bridges that are overlapping with the actin. So that's why stuff is harder. If we're too scrunched up, too squished together, we're going to hit this point where our thin filaments are overlapping with each other. So we just can't make that sarcomere any shorter than it already is. The Z lines are going to end up bumping into our thick filaments in this short, less than optimum kind of scrunched up position. Let's see. I'm just going to scroll through and see if we have a picture. Yeah, we do have a picture, so we'll trace it on there. Okay. So the cause of the summation and tetanus is also, we're just kind of touching back to that process. So the summation and the tetanus that we were talking about, the fact that we can have contractions overlapping, making our peaks higher, making us not fully relaxed, and then eventually reaching that kind of like locked out kind of position, that has to do with the calcium. So if we have calcium really saturating the system, right, and not going back into the sarcoplasmic reticulum, we're going to max out the cross bridge cycle, and we're going to just get kind of stuck there. All right. So this is that optimal length stuff. So let's take a look at what we mean. All right. So what we can see here at the bottom, we're going to have our suboptimal lengths. Up here at the top, we have like our normal range. Or sorry, in here in the middle, we have our normal range. And then out here, we have our like super stretched out range. So our increased length. Okay. So we're going to be looking at the position of these sarcomeres. Okay. So what we have over here on the y-axis, we're saying the amount of tension that a sarcomere in this position could produce. So you can see if we're down in a decreased length, this is the squished up kind of sarcomere, we can't produce that much tension. Or if we're way too stretched out, also can't produce that much tension. If we're here in our optimal range, we can produce a lot more tension. Okay. So think the easier one to understand is what's going wrong in the decreased length, the suboptimal length. So we'll start there. Okay. So usually in our optimal length, right, we have a section in the middle where we have just myosin. Then we have cross bridges on the myosin that are next to the actin, right? So they can grab on, pull that actin towards the center, making our Z lines come closer together, contracting the muscle. So that's the sarcomere we've been looking at basically the whole time. Okay. So we want to think about what physically happens as those sarcomeres slide shorter. Right? Eventually, we hit a point where the ends of those actins from either side are touching each other. Right? So that's what happened when we made the sarcomere a little shorter. We can actually get even shorter than that. So you can come up to the point where you have some of the actin, some of those thin filaments overlapping here. But what you can't do is get any shorter than the point at which your Z lines are touching the end of the myosin, right? So this is as short as you can go. So I'm gonna draw it out in case you want to draw it with me. So like, what are we looking at, right? Usually we have our sarcomere with the Z line. Draw another one. I think that's how we've been drawing it. All right, so we got our zigzag Z line. We got our actin going towards the center, our thin filaments. And then we've had our myosin here. All right. So what I'm saying is in this length, and we don't, for the decreased length, the cross bridges are less important as like our problem. So the problem we're going to run into is this gap here, right? So in order to slide a sarcomere shorter, there has to be some space for that sliding to happen. There has to be some space for that myosin to come closer to the Z line, right? So if we get to the point where we draw our Z line, all right, so we have our actins, we can even have them to the point of overlapping. But if we get to the point where I have to draw the myosin basically touching the Z line, we can't get any shorter, right? So like, if we're like this, there's no way to make this sarcomere shorter, right? There's just like nowhere for it to go because these proteins themselves aren't getting shorter. They're just sliding past each other. You cannot slide this closer. So that's what's happening when we have a sarcomere at a suboptimal length when we have this decreased length. Okay, so that's as short as that sarcomere can get. Okay. The increased length is a little, it's not too tough, but it's a little trickier to understand. Okay. So what's happening here is now we're thinking about the cross bridges. Okay. So we're thinking about these cross bridges here in our usual sarcomere as grabbing on to the actin, right? And that's how we're doing the power stroke and dragging the actin towards the center, right? We're grabbing onto the actin and we're just like pulling it, right? We're rowing it towards the center. If you have a sarcomere that is stretched out, that is past its optimal length, you'll notice of these 1, 2, 3, 4, 5 sets of myosin heads that they've drawn on here, right? Here, all 5 are overlapping with some actin. We had like 5 hands that could grab out, pull the actin. Now we only have 4, so we can't pull apart. And that's basically the problem. So as we stretch out more and more and more, we have fewer cross bridges that are near enough to the actin to grab it. So out here, you can see we only have like maybe 1, maybe none. We're so stretched out that as we start the cross bridge cycle, even when we have the calcium, like it doesn't help us that much because the myosin binding sites on the actin and actin binding sites on the myosin aren't close enough together, right? So they don't have anything to grab onto, so we can't pull towards the center. So that's why a super stretched out muscle isn't going to be able to generate enough force, because when these sarcomeres are like that, we physically can't create cross bridge cycling until we get those heads closer in so that they can overlap the thick and thin filaments. So squished up muscle, squished up sarcomere, we have no room to slide smaller. We're at our super optimal length, our way too long muscle, our stretched out muscle. We just can't grab on. That's it. Okay. Now, finally, when we are talking about a whole muscle generating force, we talked about this idea of like motor units before. So back when we were talking about the structure of a muscle, we said that a motor unit is we have a nerve coming out of our spine, essentially. So somatic efferent motor nerve going up to our muscle. And that nerve is going to split up and it's going to go to many different muscle fibers. So some number of muscle fibers. Within a named muscle, we will have several motor nerves going to it. Each of them are going to go to some of the muscle fibers there in the big named muscle. Okay? When a nerve sends an impulse, it activates all the motor fibers that it's attached to, but none of the other ones. Okay? So that was our motor unit, was one nerve and all the muscle fibers that it's goes to. So when we're thinking about a whole muscle, we want to have like a really strong contraction or a really delicate contraction, right? So you're trying to untie a tiny little knot, right? We're going to want to activate them to different degrees. We're going to want different amounts of force for different tasks, essentially. So if you have more muscle fibers contracting, greater force, okay, which basically means you are going to have more and bigger motor units contracting to create greater force. So when we are stimulating our muscle fibers, we're going to do it in like a specific order. We're going to be getting specific sizes of motor units activated in sequence in order to get the right amount of force. Okay. So what we're going to do is just increase, basically, right? So here we see those motor units. This is that concept, right? So here we have nerve X going to these slightly darker pink fibers, right? So that would be one motor unit X. And then we have motor unit Y going to some different fibers. Okay, so those are the sort of paler peachish ones. These colors look practically the same to me, but I promise you they're going to different fibers if you trace them out. Okay, so these units are of different size. So if you count them out, we got 1, 2, 3, 4, 5 of these darker fibers for motor unit X. That's 5 of them. For motor unit Y, we have 1, 2, 3, 4, 5, 6, 7. Motor unit Y has 7 fibers here, so it's bigger. So if we stimulate nerve X for motor unit X, we're going to get some amount of tension. If we stimulate motor unit Y, this other nerve has more fibers, we get more tension. It's bigger. If we stimulate them together, we're going to double up. We're going to get a lot more tension because we can basically just add them together. Okay? So this is basically what we're going to be doing as we're trying to create more tension, trying to contract our muscle more strongly. Okay. So in terms of motor unit recruitment, if we have more fibers, we're creating greater tension, more force, right? Like we're lifting something harder. Okay. So we're going to do that by recruiting more motor units so that we can add them all together. Okay. So activating the motor neuron activates all of its muscle fibers. We increase in tension if we activate more muscle fibers. So if we have a motor neuron with more muscle fibers attached to that nerve, greater tension. If we have a smaller one, less tension. We do not always want to be doing everything at maximum strength. If you're just opening every door like real weird, right? You don't actually want to do that, right? You want to adjust for how much force you actually need. And for some tasks, right, you want to use really delicate touching movements, right? Like, for example, when I am dissecting, right, like I don't want to just be slashing everywhere. You're going to get some real wonky looking dissections in there, right? Like I got to do some little tiny delicate scalpel movements. So if you ever become a surgeon, right, you might be really just wanting to practice using your teeny tiny small delicate small motor units. Okay. So small motor units, Small for a reason, actually helpful for those small, delicate movements. Muscles for strength, really large motor units. Great if you're lifting, right? Great if you're doing real big, heavy exercises. If you're trying to push a friend's car up the hill because it's slipping in the snow, you want those large muscle motor units. Okay. All right. So small ones, delicate movements, because they're small. We're also going to have skinny little fibers. Large ones for big strength movements. That's going to allow us to create greater force. So this would also go along with the fiber diameter. So when we have little motor units with only a couple little muscle fibers, those muscle fibers are also probably skinny and tiny. If we're looking for a motor unit with big, strong movements, those muscle fibers are probably going to be wider in diameter. They're going to be bigger, chunkier, because we're trying to generate a lot of force. Okay. So the order that we recruit them is in terms of the size, right? So we're going to try to be using the least amount of force possible to do whatever task it is, right? We're not going to try really, really hard to lift this mouse, right? Like I'm not going to go with my large motor unit first, right? I'm going to be slowly ramping up, or not so slowly, depending on like what your mind has decided. But you're going to start by trying to use only a little force, and then if you have to, use greater force. So you're going to start by activating those small motor units. The small motor unit is enough. You're going to get a slightly larger motor unit, until you're activating all of your motor units, including the large ones. Okay. This does have a physiological reason, which is that the larger neurons are harder to depolarize. But it also makes sense from a practical perspective of what you want your body to do. Okay. So here we see some motor units of different sizes. Let's see here. All right. So here, W is some nerve from your brain in your central nervous system. All right, so that's central nervous system stuff. This is linking up to our actual somatic motor nerves, which are X, Y, and Z. All right, so we can see X is the smallest, Y is in the middle, Z is the biggest. So we can see what happened when W fired. First, we activated X. It only took a little bit to depolarize that, right? Also helpful it goes first because we want to kind of ramp up our strength. So we activated X. Then we activated Y, which was a little bigger. Since we're still activating X, right, we can add them together. So X would have had this much tension, Y would have had this much tension, but they're both going at once. So now we've got that much. And then we could add on Z, our big one, at the end. So that's just the order that we activate here, our motor units, and this is called the size principle, which is just that we do them in order of size. Okay. So that is it for the content we are going through. Did print out like a little worksheet on the cross bridge cycle. You can stick around and work on that, or you can take 10 minutes to yourselves, go get lunch. But I'll have those up here, and I can post those for you on Brightspace or in your folder so that you can use them to practice later if you want. Yeah, like yeah. Well, what I'm wondering is like whether that's about what I'm going to do, but I see I have one more question. Yeah. Like when you got like this going on. Where are you going to be? I'm curious. Oh, like when you want to get up and you need to move?
Yeah.
I would think that's not like so much at the muscle level as it kind of like the level of your okay would be my guess. Okay. Yeah. But if it's like switching stuff, then I think that would be like overactivity of the nerve itself going. Really, did you go to the live stream stuff? Is it not there?
Under the live stream.
Oh, yeah,
I know that they're in like in Brightspace, they have like a lecture recording little link, and
Okay,
you have to
yeah.
sit until like the end of the endocrine system.
Sure, I'll add them, but just so you know, when you find me, right, like if you go to that stuff, you can go to like all of face. You could just go to past live streams, so they're all up like immediately after class. So I make a playlist just to pick them out for you, so that you don't have to be like, what date was that lecture? But they are always up.
Okay, perfect.
So I'll go through and add those. Fine, you got it.
I have a few questions.
Yeah.
So the pre-ganglionic sympathetic, does that start at the lateral horn or the ventral, or are they the same thing? 'Cause on the slides it had it up, and how they.
Frankly, the answer is I don't really care. Lateral.
Okay. Okay.
Yeah.
And then on the cosmic cycle, the IFP and the pad, like at the end of it, is also in substitute. But it's not bound to it. When it's like in the back position.
Like at the beginning of it before it starts, yes, but like as you start to do it, then we're moving towards the lower.
Okay. And then, okay, the twitch versus contraction. So a twitch, when it's isolated, is when it shortens. Is that when the paper shortens or the full?
The twitch is as the start shortening. If the whole fiber shortens, that would mean the stuff at the end. It's like, so that would be like.
Okay, so a twitch is just one muscle fiber?
A twitch is the response to like.
Okay. Okay, so you can have an isotonic twitch, but the whole muscle itself might not.
The isotonic twitch would make the muscle contract, because that's the one that moves it. Right?
Okay.
Yeah, the whole thing. Whereas the isometric one, you shuffle.
Okay. Okay. I think one of the hypothetical question of like hypothecation of thyroid hormones, and would that also decrease the TRH and the TH if it was? But is it in the body or is it just in?
If it's of the thyroid hormones, like at the thyroid, it kind of depends like why. But probably that is coming from like the hypothalamus, right? But because that's all, right?
Yep.
Right. So we're talking about like this stuff, right? So if we have like low concentration of thyroid hormones, like maybe something comes to the thyroid, but likely a response to like
but that's like very
from the hypothalamus.
Yeah. Okay. Yeah, that makes sense. Thank you. And then is there any way that expense? Oh, okay, perfect.
Yes. Yep.
Just a quick question. Is the all three or like the all unit 3 slides, is that available to students?
No, but they're the same as the things in your folder.
Okay.
Yeah. They're just broken out. Like I like having them in all one giant thing.
Me too.
I would. Yeah. I just copy pasted them all together. That's all. Which email?
It was just a quick email, I just thought the subjects. It's like, no, it was an admin question.
Well, you want to just ask me?
Sure, I was just curious, just the same, I know that I believe we get to retake one of the unit exams by the end of the semester.
Yep.
Is that,
Not for that.
Not for an admin, okay, I was just asking, you know, if you